Good morning, everyone. Can you hear me? Okay, perfect. Thanks a lot for joining on a Saturday morning early. I'm going to talk today. So I'm Gaspard Tissandier. I'm working at Rutgers University, and I'm going to talk about crime prediction. So I know we're in a conference like full of philosopher, ethicists, and talking about crime prediction is a pretty touchy subject. But bear with me, that can be interesting, and I hope and I will try to convince you that we can do that for the good, like actual ethical good. So, what are the motivations of this paper and project? So, I work for the New York Public Safety Collaborative, which is basically an anchor institution based at Rutgers and in Newark, New Jersey. And the idea of our project is to do what is called data-informed community engagement. And so we are providing data analysis, predictions, insights, and many other data tools to community organizers, partners, and a lot of associations. The goal of the NPSC is to increase public safety in Newark, and we are trying to do that by partnering with like the right organizations. So we've been doing that for more than 5 years. I've been on board for like around 2 years. And after all those meetings, discussions, and interactions with our community, we reached like a few conclusions. So the first one is when it's time to talk about crime prediction and crime policy, our partners most of the time have a very good overview of crime structures and dynamics in their area. So doing crime prediction might not be like the most like pure prediction might not be the most advantageous use of AI, purely prediction. Secondly, and most importantly, most of our partners, if not all of them, really wants to understand what we're doing. So one time we tried to present some prediction made by like some very fancy deep learning model based on heat map, and all of them looked at us and were kind of like, sorry, we don't understand. There's no point into that. Can we just like get back to like more simple analysis, regressions, and this kind of KD, for example? We're like, sure, yes, we're going to do that. So what is the idea? The idea is that they partners, organizers want to understand how we're reaching predictions. And most of the time, they're going to use those predictions and actually they're going to use the model to figure out what's going on and mostly to try to find levers and variables to act on in their daily implementation of policies. So, there's like a lag in the mic. Is it okay? Okay, perfect. Thank you. Yeah, we're fine. So, it's better. There was like quite a lag. Okay, we're good to go. So basically, none of these goals like basically to provide interpretable models and to try to provide insights and understanding and actually knowledge about situations is actually achievable without using understandable models. And I'm going to explain a bit later what is actually understandable machine learning models. So we can see like a rise in the use of machine learning for crime predictions. So this is like a very simple representation of like the numbers of papers with in the abstract or the title, machine learning and crime prediction. And as you can see, there was like a big rise since 2022, and then it's kind of like plateauing. But we can observe like a trend among like public associations and also practitioners and researchers for the like a big call for the use of understandable machine learning models. So why and how and especially when should we use understandable or like interpretable or explainable machine learnings? The first elements pointed by Gimenez and Kim in 2017 is that when we have predictions which are for high-stake decisions, so there is like big consequences, we can talk about, for example, prediction of disease like we saw like right before, or for example, crime prediction, you will need to have some model that you can actually understand. The second point is when like the prediction process is not perfectly mastered. So when we have, for example, some challenges in the prediction, it's not like perfect. We're gonna need to have like understandable models. So for example, handwritten recognition, it's not like a big problem because it's well mastered. So we don't need to have like interpretable model. But in our case, for crime prediction, this prediction problem meets both criteria. So basically, it's actually very high-stake decisions. We saw all the literature in ethics and AI regarding that. And we saw all the articles in the New York Times, the Guardians, about like all the issues using AI for crime prediction. And also, it's a very complicated problem in terms of machine learning application, purely and simply. So let's talk a bit about like what is it to do understandable AI. There is basically two big branches in the literature. The first one is going to call explainable machine learning. So you take a very complex model, think about deep learning, think about gradient boosting, random forest, something that you cannot like make sense of as a human, and you try to find a way to explain it. First solution. Second solution, the one that we're going to take in this paper and in this work, is called interpretable machine learning. So the idea is that you're going to try to find simple models that you can fully understand, and you're going to use them to do your prediction. Why do we use mostly interpretable machine learning model? Because basically, trying to represent something very complex in a very simple way is most of the time misleading. It's not going to give so much insight about the situations, and especially doesn't build trust between researchers, machine learner, and practitioner. That's a problem. So let's try to organize a little bit our idea regarding that. Why do we need interpretable machine learning? The first one is to do some model debugging. It's actually very important in crime prediction. Why? Because if you have, for example, some issues with bias or discrimination by the model, you want to be able to point out exactly where it went out or it went wrong. Is it like, for example, targeting of certain neighborhood? Is it targeting of certain population? You have to be able to explain all of this to be actually to have like a nice interpretable model. The second one is building trust. So basically, we are in an interaction between people who are not able to master very advanced statistical models, and you want to say, okay, we are building those models, but we want you to understand what we did from the beginning to the end, building trust. It's very important to understand that it's not a guarantee to build trust, it's a possibility to build trust with interpretable machine learning. After that, we're going to have to decide whether to intervene or if to intervene. So basically, the idea that maybe sometimes it's not the best to actually put some policies in action. And the last one is going to be to decide how to intervene. And this is like the most crucial point of this whole understanding of interpretable machine learning. Actually, most of the time in our observations, practitioners are going to just use the machine learning modeling and like every statistical modeling to decide how to intervene, to try to get insights and knowledge and make them actionable through implementations and public policy. So in this paper, we defend the idea that based on our experience, quite long experience working on these kind of questions, we defend the idea that it's not only desirable, but it's actually necessary to use interpretable machine learning when you're doing crime prediction or you're working on any public policy related high-stake decision. So what are we talking about when we say we need like some interpretable machine learning? There is like mostly 4 elements that we are that we are trying to get in a model. The first one is sparsity. Your model has to be small. So when I talk about like a small model, I talk about a dozen elements, a dozen coefficients, a dozen rule, like a dozen splits in a tree, something very small. Then you have what is called simulatability. So basically, you have to be able to kind of understand it fully as a human. So basically, you have to think, oh, sure, yeah, I understand how this model works, and I'm able to explain it easily and simply to somebody else. Then you have modularity. So basically, you have to be able to isolate some portion of the model and to make sense of them. This one is very important. For example, regressions are great for that because you can isolate coefficients. Decision trees are not great for that because you have to make sense of the whole tree to be able to understand one space. So decision trees, as you understand, are not going to be our best fit in this case. And the last one, which is going to be more like in the design of the system, it's called domain-based features engineering. So basically, it doesn't make sense to present some features and to try to interpret them if they don't resonate with actual knowledge used by practitioners in real life. So all of these points are bringing me to the research questions of this paper. which is basically, sure, yes, we should do interpretable machine learning, but can we? Is it as efficient to use interpretable machine learning algorithm rather than to use, for example, fully black box model or like more simple statistical models? This is what we check in this paper. It's mostly like a machine learning model benchmark paper. And I'm going to show you a few models output after that for you to understand like the whole same setup. So what is our setup? We are doing crime prediction. So we organize the prediction of this paper based on what our partners told us would be useful. So the whole setup is not driven by the statistician intuition. It's actually driven by what our partners actually needs in their daily base. So we are doing prediction for 5 different type of, 5 different type of crime at the weak block group level. So for the non-Americans, a block group is basically around 40 blocks. So it's around like 1,500 inhabitants in a given city. So we work in Newark, New Jersey, on the data sets based in our city. And as you can see, we have strong class and balance. So we do some smart sampling to recalibrate that. And we train all the models on the same subset of features. Finally, since we have strong class and balance, we are fine-tuning the F1 score for our models to maximize the F1 score. So which kind of data do we use? We use 4 main type of data. This is not revolutionary. So the idea is to really try to use what is accessible to actual practitioners. So for example, you can see machine learning papers which are using ambient population based on mobile phone data. This is great applications, but like most of the time, it's not going to be available for practitioners. So in our situations, we use 4 main type of data: historical crime. So we use that to build like historical dynamics of crime in given neighborhood. The built environment, so presence of businesses, presence of parks, public amenities, public services, and many others, socioeconomic factors out of the census. And finally, the weather. So all those data are basically linked to for either sociology theories or criminal justice theories or criminology theories. So the idea is to, when some variables are going to pop in the model, we're going to be able to make sense of them and to propose some actual policy implementation based on that. Great. Now we get to the 4th point in terms of what is desirable in an interpretable machine learning model, which is the domain-based features engineering. And in our situation, we are doing a fully domain-based variable selection. So what we did is we got all the variables that were available to us. We sat down with our partners and we asked, what do you need? Which one do you want? Which one do you make sense of? And we actually restricted the numbers of variables from around 269 to 100 features, variables. So which kind of model are we going to use? We're going to basically compare pretty standard machine learning models, so penalize logistic regression, decision tree, with like black box model, which should be our basically our benchmark, our best performing model, with like more new generation, highly interpretable models. So what is called the EBM, it's basically some generalized additive model. So we kind of like build some function for every features independently. One called risk slim, which is a very nice algorithm outputting some risk scores. And finally, an algorithm called Cirrus, which is basically extracting rules out of random forest. So you have a little table right there, which is explaining if each model is actually fulfilling our desirable points. And we can see that risk slim and Cirrus are actually our best pick in terms of like what is needed for interpretable machine learning. So going to the results, we're going to start by assessing if doing some domain-based feature selection is actually useful. So we limit our set of model for now of the standard machine learning model and the extreme gradient boosting. And as you can see, there's basically no huge drop in accuracy or sensitivity or even the F1 score when we are actually using, can I point with that? Yes, I can. So basically, if I use like the full subset, so 261 features down to the interpretable subset, so 103 features, there's no huge drop most of the time, if not at all, in the performances of the model. Now we switch to what is it to actually implement sparsity in our model. So we start with the classic penalized logistic regression, and we try to understand how it is to go from the best performing model, which is going to be at the top of the table, down to 10 features, which is what is actually recommended in terms of sparsity. As you can see, there's an actual trade-off in the sparsity of the models for classic penalized regression. So maybe penalized regression will not be our best pick in this situation. And finally, and most importantly, there is like the full assessment of all the models. So we're going to take a bit of time to check the results. Basically, you have our classic penalized logistic regression, decision tree, extreme gradient boosting, explainable boosting machine, the risk slim, and the cirrus. And we are comparing the performances on here, like vehicle theft and aggravated homicide. Why? Because it's would be a bit boring to go through 5 different types of crime, and it's not the point of the paper. And the point of the paper is to show you that basically using interpretable machine learning models is not an issue regarding performances of the models. So as not as we expected, basically, what is most of the time the best performing models are actually the penalized logistic regression. So simple models, simple setups are actually the most useful in this situation. Then what we can observe is that how like kind of like best pick models, so risk slim and cirrus, are actually pretty good performers and are still doing great, even if they are like very simple models. And I'm going to show you what they look like right after. But what is the main takeaway of that? So you're going to tell me, nice, your accuracy is very low, the sensitivity is very low, the specificity is very low. Sure, yes, that's the point. Crime prediction is actually a very complicated prediction problem. And most of the time, it's going to be, if you have like very high accuracy in crime prediction, it's going to be because you have like a very specific setup. So what we saw in the literature, for example, is researchers predicting crime on, for example, 6 months or at the city level. And it's not complicated to approximate a Poisson distribution. But if you go more into details into like what is actually needed by practitioners, it's going to be much more complicated to predict crime. So that's a bit the point. And that's the main takeaway of the paper. Crime prediction is complicated, and please don't trust anybody else who's saying that to you. And one of the last points I want to make about these tables is that we have like a decent sensitivity without being great. We're capturing more than half of the positive class, so actual crime in our setup. Why do I point that? It's because it's to say that when we're gonna go to the interpretation of the model, we can expect the model to actually capture some signal, and we're gonna be able to make sense of the interpretation because it's not only noise. There is actual signal, and we can interpret that. So I'm gonna show you. I'm gonna show you 2 models, actually the risk slim and the cirrus, just to make sense of all of this. So the first one is risk slim. As you can see, it's a very simple scoring points table, and then you have like you basically multiply your variable with the scoring system, which is only integers, and then you refer to the table to see what is your actual potential probability of having crime in a given block group. As you can see, we capture pretty well the structure. Right up there, we have the average observation, and down there, the average prediction. We kind of capture pretty well the structure of crime. So I'm pretty confident into the fact that the model is actually capturing signal and not only noise in this situation. I can share the slide at the end, no problem. And we're going to switch to what is called cirrus. So very nice model, which is more like rule-based. So it's not only scoring, but it's more kind of like take a given variables, split it as in a decision tree, and then extract this decision rule to actually take decision. This is a pretty powerful algorithm. Why? Because it's able to manage nonlinearity in relationship in variables, which is pretty efficient in situations where we have like very unequal distribution, for example. So once again, we kind of capture pretty well the structure of crime in Newark, and it's pretty positive. And finally, the average F1 score of all the models on different type of crime. And as you can see, there is no big drop in the F1 score when we use interpretable machine learning model. So thanks for your attention. Main takeaway points. Crime prediction is complicated, and you should consider it as it is. Crime prediction, if it's complicated, shouldn't like pure prediction. So kind of like we use a full black box model to, for example, allocate police resources is never a good idea. Why? Because it's a complicated task. So most of the time you're gonna miss the points and just justify unethical action based on, oh yeah, the model is saying so. So yeah. So the point is that doing crime prediction is you should take some time with that. Second one, it's possible to use interpretable machine learning model without having like big drops in accuracy. And third one, I think for every public policy application, we think you should always use interpretable machine learning model. It's not only desirable, it's necessary, and there is no other way than using interpretable machine learning for high-stake decisions. And I would love to hear your question. Thanks a lot for your attention.
Thanks so much. I think we have time for one question. Yep. Oh, yes.
Thanks for the really great talk. So you alluded earlier in your talk that there's been a lot of pushback against these predictive policing models from a social justice perspective. But then you argued that maybe these models can be good. So could you elaborate more on your views on that? Because this is something that I'm wrestling with. Thank you.
Sure. Thank you for your question. Very good question. And thanks for pointing inconsistency. I think machine learning models are actually most of the time good for understanding situations more than doing like amazing prediction on any system. If you want to do pure prediction, first, most of the practitioners are going to be able to do them themselves pretty accurately. And it's not complicated. It's better to use like pretty standards, for example, regression, like time series model to do crime prediction. What I'm defending is the idea that if you want to use machine learning, you should use machine learning mostly for understanding situations, for getting knowledge and insights out of situations. And that's my point. And only in this situation would using machine learning models would be useful. You're welcome.
Okay, one more. Go ahead. One more. No, it's okay. We've heard a question from her, so we'll take one from you. Is that all right?
I'll keep it super brief. Can you define crime?
Oh, sure. My bad. We're talking about.
Sorry. I'm going to take one small one onto that. Can you define crime briefly? And then also, as part of explaining that, talk about data cleaning, pre-processing, and talk about how, the data that you received, how you treated that.
Absolutely, very interesting question and necessary because your data cleaning is actually most of the work in this situation. So when we define crime, we talk about police sources, unfortunately. It's data coming from the Newark police departments. And we're talking about occurrences of crime. So it's like every crime which is validated either by the police department or the court. So it cannot be like only like a 911, 911 call. Then in terms of the data cleaning, we're doing some scaling of the variables. The variable selection is done through domain-based, as I told you before. Except for that, missing values or absent values are treated using median assignations. What else? That's pretty much it.